And greetings to you watching this video. This is Prudvi. I'm from EC department and my roll number is 2440100491. And here is my continuous alternative assessment of antennas and wave propagation. And begin with my topic is space wave propagation. Here is a title page. And to begin with the definition, it's a wave propagation where the electromagnetic wave travels through the troposphere via direct and ground reflected rays. It means the first layer, which is above Earth, is troposphere. Beyond that, there are many layers. It's like troposphere, stratosphere, mesosphere, thermosphere, and exosphere. The first layer, which is troposphere, the wave propagation uh, is done, and the wave travels through the troposphere. And the frequency range of this is 30 to 300 megahertz. It's very high frequency. Its megahertz is something like 10 power 6, and ultra high frequencies below. The range is 300 megahertz to 3 gigahertz, and above wavelengths are too short for skywave reflection. The key distinction is it's like underground waves or skywaves. Space waves are fundamentally limited by Earth's Earth's curvature and antenna height. This is something different from other wave propagations. It's something different, like it's here the Earth's curvature and antenna height plays a major role, and it is a electromagnetic spectrum and wave types. The basic one is ground wave propagation, which we generally use in a daily day life, obviously, and sky wave is a low frequency or minimum frequency is less than 30 megahertz, and skywave is like 3 to 30 megahertz. It's a high frequency band. The next one is space wave propagation, direct plus reflected rays, which are used in TV, radar, 5G, and many other um, high networking communications. So to begin with that, here is a formula, Maxwell's equations, which are used to implement the space wave propagation. Del cross E is equals to mass of change in magnetic flux density. With change in magnetic flux density with respect to time, and del cross H is equals to current density plus electric flux density, change in electric flux density with respect to time, and the line of sight range in the radio horizon. It's like geometric loss formula. Geometric loss formula is line of sight range. So it goes like d is equals to under root RHT plus under root RHR, where R is the Earth's radius and H is the antenna's height. So the line of sight distance between transmitter and receiver. The distance between the transmitter and receiver is calculated using the radius of Earth and antenna height. As I initially mentioned, space wave propagation is done by using antenna height and Earth's curvature. And here is Earth's radius, and that is how we calculate the distance between transmitter and receiver. The effective Earth radius factor is approximately is equals to 4 by 3 accounts for standard atmospheric refraction, extending range approximately 15% beyond the geometric horizon. And radio horizon for transmitter at 10 meters height, it's like 11 kilometers, at range of 10 meters. And radio horizon when height is raised to 100 meters, it's 30 kilometers and range at 100 meters. Standard effective radius multiplier for refraction. So the K factor is 4 by 3, something 1.33 bar. And here is a two-ray ground reflection model. Two-ray ground reflection model is like the directed ray, the direct ray plus reflected ray. The received signal is a superposition of direct ray and ground ray, scaled by reflection coefficient rho. At large distances, path loss is directly proportional to square of d square. So here, not d square as in free space. So gamma depends on um, grazing angle, polarization, and ground permittivity. And epsilon r is approximately 15 for average soil. Epsilon r here is relative permittivity. Relative permittivity is a permittivity of a certain medium multiplied by permittivity of free space. And here the relative permittivity is 15 for average soil. And d power 4 roll off is a critical design constraint for terrestrial microwave links. And here are the Fresnel zones and clearance criteria. The first one is understand Fresnel zones. Basically, uh, ellipsoidal regions surrounding the LOS line of sight path, obstructions within the first Fresnel zone cause significant diffraction loss. So, yeah. And the second one is apply the clearance rule. Keeping 60% of the first Fresnel zone radius clear, R1 is equals to under root lambda d1 into d2 by d1 plus d2, where d1 and d2 are distances from each end to the obstacle. And the third point is quantify diffraction loss. The knife edge diffraction model, ITU RP, I mean RP 0.526. This is the model, and it quantifies loss when obstacles intrude, essential for microwave link planning. And antenna parameters should be like antenna parameters for space wave links are like gain. Gain is it's like product of directivity and efficiency. Parabolic dishes achieve greater gain. It's great. I mean, the gain would be greater than 40 decibels at microwave frequencies. And effective aperture. Effective aperture is gain into lambda square by 4 pi, which links which links received power directly to antenna size. And polarization, horizontal versus vertical effects ground reflection. Cross polarization discrimination is critical in frequency reuse schemes. And common antenna types are like which often uh, do space wave propagation like half wave dipole, Yagi Uda antenna, horn and parabolic reflector, each suited to specific frequency and gain requirements. And propagation model link budget. The first one, Frisch transmission equation. PR is equals to PT CTZR and lambda by 4 pi d whole square. This is the foundation of every RF radio frequency link budget and relating transmitted power, antenna gains, wavelengths, and distance to receive power. And fade margin. Fade margin is typically 20 to 40 decibel added to the link budget to ensure 99.99% availability under multipath fading and atmospheric detecting conditions. And rain attenuation. Due to the um, um, yeah, natural distortions, the attenuation happen, and this often impacts and affects the output, and there will be an effect on spacewave propagation things. So significant about 10 gigahertz and model via specific attenuation coefficients per ITU or P8.838. When U is 530, ITU or P.530. Standard model for terrestrial links accounting for multiple path fading and rain attenuation. And when you use ITU RP 2001, wide range terrestrial propagation covering 30 megahertz to 50 gigahertz, including ducting, troposcatter, and hydro material effects. So it's better to use the good one like ITU RP 2001, and that's the end of the spatial propagation. Thank you.